Now, the reason I started with this picture, I'm always in awe by the spectacular super blooms in Southern California that was brought about by this year's heavy rains. And it raises questions because I keep hearing people say ecosystems are falling apart. Well, this looks like the heavy rains made the flora very happy. And so the question is climate change a good thing or a bad thing? Are these heavy rains a bad thing? Well, it depends on your focus and your circumstance, because other headlines were showing how people were flooded and it was devastating and it was a crisis. Now, likewise, in the century's most influential books, the structure of scientific revolution, Thomas Kuhn wrote, someone could mute themselves. Thomas Kuhn wrote, philosophers of science have repeatedly demonstrated that more than one theoretical construction can be placed upon a given collection of data. So accordingly, those of us who are trained as ecologists, like myself, as well as most geologists, we've been trained to always embrace multiple theoretical constructions, otherwise known as hypotheses. Now, competing hypotheses for the recent return of Tulare Lake in Southern California is another case in point. When the Spanish first arrived, Tulare Lake, as seen in this 1875 drawing, sustained Western North America's greatest density of Native Americans due to Tulare Lake's vast nourishing ecosystem. However, the Spanish colonizers removed those tribes, and the lake slowly disappeared due to a combination of a drying climate and the colonizers' desire to convert Tulare Lake into agricultural fields. But with this winter's heavy rains, Tulare Lake has reappeared, and several news outlets have featured a segment of the native Yokut people celebrating the return of Tulare Lake, for which they still had strong cultural ties. Their traditions passed down the belief that the lake one day would return due to a natural wet cycle. But in contrast, NBC, NPR, and other media outlets portrayed the rains and the return of Tulare Lake is a prelude to how CO2-driven global warming crisis is threatening farms and increasing floods. So which narrative is accurate? Which theoretical construction explains Tulare Lake's return? Now, I confess I favor the Native Americans' perspective because it is supported by historical data. California's Central Valley was once considered a marshland, not due to floods from a warmer climate, but due to a wet cycle during the cooler 1700s and 1800s. Now, similarly, there are many hypotheses about the causes of today's warming Earth in extreme weather events. Most scientists doubt a global warming can be explained by insignificant increases in solar heating. However, most believe it is better explained by how much heat is being trapped. For an analogy, human metabolism generates a constant rate of heating at about 58 watts per meter squared, producing a body temperature of 98 Fahrenheit. And in climate science, everybody uses watts per meter squared, which is simply a measure of energy per second. More watts, more energy. But if that heat doesn't get trapped, our body cools both rapidly and uncomfortably on a cool day. However, a thick blanket can trap heat and delay cooling, thus keeping us warm and cozy, or sometimes even too hot, despite colder surrounding temperatures. So today I want to examine three powerful climate dynamics that often get confused that trap heat and cause warmer temperatures. The primary focus for the past 3 decades has been the greenhouse effect. Indeed, if greenhouse gases did not trap some of the heat delivered by the sun, the Earth would lose heat to cold outer space so rapidly, the Earth's average temperature would plummet from our current about 59, 60 degrees Fahrenheit average to below freezing, and all life would stop. So clearly, greenhouse warming can be highly beneficial. But for how long does that heat get trapped? And does the greenhouse effect almost explain warm temperature extremes? Well, surprisingly, greenhouse gases release the energy from the infrared radiation they absorb in less than 1 second. So the greenhouse effect requires a more extensive understanding, which I hope I can clearly and simply explain in this presentation. Number two, in contrast to the greenhouse effect, the extreme temperatures of a heat wave, like they're having in Texas, are caused by heat domes. Now, heat domes don't trap radiation like a greenhouse gas. Instead, heat domes suppress the normal convection process that carries solar heated air up and away from the surface, where it can then be radiated back to space. And three, greenhouse infrared radiation does not penetrate into the ocean any deeper than a few microns. Now, I don't know how many of you are familiar with microns, but 1,000 microns can fit on a sharpened pencil point. It is the ocean's salty subsurface layers that suppress ocean convection and trap ocean heat for days, years, and centuries. Thus, the ocean stores 1,000 times more heat than the atmosphere. So by acting like an old-fashioned hot water bottle that many of you are old enough to have used, like my grandmother, it can keep they use it to keep warm at night, and the trapped ocean heat also warms our climate in the same dynamic. So people, especially children, who don't understand how the greenhouse effect works, are too easily frightened right now by every unsubstantiated hypothesis claiming that more CO2 is causing a catastrophic crisis, that every weather disaster, and soon there's an extinction of all life. And a lot of these kids don't see a future for this reason. So to support our critical thinking skills, I hope to instill some greenhouse basics illustrated by this graph, and that is used by all climate scientists. A solid understanding of it will almost make you an expert on how greenhouse effect works. Now, it represents the settled physics, the one aspect of climate change debates that 99% of all scientists studying climatic changes, from alarmists to skeptics, will agree on. But first, understand that the atmosphere's density also moderates how well greenhouse gases trap heat. Now, this can be seen if we compare temperatures on Earth with Mars, and they both have about the same length of day. At the Earth's equator, the temperature averages about 88 degrees Fahrenheit at noon, but due to very humid tropical conditions, greenhouse conditions, temperatures will very slowly cool through the night, dropping to just 73 degrees by morning. On Mars, which has a very, very thin atmosphere with almost no water but 92% CO2 concentration, temperatures can reach 70 degrees at noon along the equator, but with such a very thin atmosphere, the greater molecular spacing allows infrared wavelength to escape more easily. So despite Mars's much higher CO2 concentration, Mars rapidly cools through the night to a minus 100 degrees Fahrenheit. Now, I'm going to spend a little time on this graphic because it's really key to our understanding. This graphic represents the broad spectrum of infrared radiation wavelengths that the Earth emits back to space, allowing the Earth to shed its daily absorbed solar heat. The smooth dark blue curve represents the strength of all the infrared wavelengths that a body is expected to emit at the Earth's surface, average temperature of 60 degrees, if there's no atmospheric interference. At the Earth's average temperature, the significant wavelengths that carry away infrared heat range from 40 to 4 microns, as noted by the scale at the top. For non-physicists, which I assume most of you are, it is helpful to think of infrared wavelengths as roadways carrying away heat. The peak of the curve represents wavelengths between 20 and 15 microns, which act like interstate highways carrying the greatest flow of heat away. While wavelengths of 5 or 40 microns act more like bumpy dirt paths, providing very little heat transport. The black jagged line represents how much energy each wavelength is actually transporting out to space as observed by our satellites. The difference between the dark blue and the black curves represent how much heat greenhouse gases prevent from escaping via each wavelength. The greater the difference, the greater the greenhouse effect. And this is all excellent data. It's all settled science, and 99% of everyone agrees on this. However, this data does not determine how long infrared heat will be trapped for or how it affects Earth's temperature. Greenhouse gases only cause detours for escaping heat, not permanent heat traps. Those detours simply delay the time needed for the heat to escape to space. It controls how quickly we cool. But not understanding this crucial point has led to many absurd theories that rising CO2 is causing a climate crisis and extinctions, and it's causing much weeping and gnashing of teeth, I should say. Now, we can easily see why carbon dioxide is worrisomely considered such a powerful greenhouse gas. The areas highlighted in red illustrate how much infrared energy that CO2 absorbs and redirects back to the Earth's surface. CO2's biggest effect is centered around 15 microns, wavelengths that would otherwise serve as the major interstate highways, which heat would otherwise escape back to space. However, CO2 either emits or transfers any absorbed heat in less than 1 second. CO2 emits the absorbed wavelengths in all directions with half directed back to the Earth's surface. And it is that redirected heat that maintains the Earth's warmer surface by reducing the rate of cooling. Now, CO2 also rapidly transfers its absorbed heat via collisions with other atmospheric molecules that cannot radiate the heat away like oxygen and nitrogen. All these dynamics delay nighttime cooling and force escaping heat to take various detours. In this illustration, a green line has been added so you can distinguish the amount of peak heat absorbed by CO2 versus the heat also absorbed by water vapor. And the red line, if you notice along the bottom of the dip there, it is added to show by doubling CO2, it will only increase the amount of redirected heat by 1% or 2 to 3 watts per meter squared. Now, water vapor absorbs much more heat from a wider range of wavelengths. Dry desert climates in the Antarctic desert lacking water vapor will experience a very reduced greenhouse effect because there, heat can escape more freely via the wavelengths water vapor would have otherwise intercepted. So while daytime temperatures may reach over 100 degrees Fahrenheit in the Sahara Desert, temperatures rapidly plummet by 50 to 100 degrees during the night, despite our CO2 effect. And importantly, something that gets overlooked is there are also wavelengths that always allow heat to escape freely and instantly to space at the speed of light, providing atmospheric windows that allow about 15 to 20% of the Earth's absorbed solar energy to escape without delay. And these atmospheric windows are what our satellites use to measure stuff on Earth. Now, that window also provides a detour for redirected greenhouse heat to finally escape. Although the redirected energy from water vapor and CO2 are transported via very specific wavelengths, after warming the surface, the Earth's solid surface, unlike greenhouse gas molecules, then emit that heat via the entire spectrum again of wavelengths. So 20% of the redirected greenhouse energy can now escape back freely through the atmospheric windows. So this process repeats and continues throughout the night, gradually dropping surface temperatures lower and lower back to the early morning minimums. So despite the recycled energy that delays cooling, the greenhouse effect doesn't trap heat for very long. Furthermore, the greenhouse effect is much reduced in the colder polar regions where CO2 can have a cooling effect. Here's another diagram by atmospheric physicists showing that Antarctic's dry climate, as well as other polar regions, exhibit a very different dynamic, a negative greenhouse effect. Here, the red curve also represents what's expected strength of infrared wavelengths that emanate from the Antarctic surface for the average temperature in October. The black line represents what satellites actually observed. So first notice where we saw a lot of water vapor absorbing heat. you'll notice in Antarctica's dryness, there is very little absorption in wavelengths, and that would usually be intercepted by water vapor in warmer climates. And more striking, notice that for wavelengths dominated by CO2 that I've highlighted in red, heat is radiated away more than is expected. Thus, you had a 2015 paper review study reported in Antarctica, CO2 enables more heat to escape to space than expected from Antarctica's cold surface. And they warned for the cold Antarctic continent, care needs to be taken when discussing the direct warming effects of CO2. So too often, the media only reports the sensational narratives from scientific studies. And they speak of what's possible looming catastrophes with Antarctica melting and rising sea levels flooding humanity. But rarely do they report the equally possible good news. So I would bet that most people here have never been made aware of the many studies showing the negative greenhouse effect, or that Antarctica researchers are split 50-50 on whether or not CO2 is causing any of the observed changes in Antarctica. So with that, I'm going to open up for questions for 5 minutes. No questions? I can't see anybody. Did everybody get muted?
Yeah, everyone is muted, but I don't see any
Okay,
question on the chat. Yeah.
If the CO2 is not causing the ice sheets to melt, what might cause them?
I'm going to hopefully give you a sense of that from the way the oceans are working. The amount of heat that is stored in the oceans has a big impact. There's circulation changes that bring heat up and to the polar regions. If you really 35 million years ago, Antarctica started forming its glaciers when we had a whole lot of CO2, and it created an amazing ice sheet long before Greenland did. And so it's not like just an atmospheric sense, it's a way that ocean circulations cut off the transport of heat to the different polar regions.
Are you worried about global warming?
I am not. I think I would worry about any extreme kind of weather that happens, but I've grown up with hurricanes or tornadoes, depending where I live. And I've experienced heat waves since I was a kid. Those things you got to take good precautions on. But at this point, I don't see enough evidence emerging that blames any of these catastrophic events on rising CO2. I think CO2 has a greenhouse effect. I don't think it's a crisis.
I think there was a question from Herb on the chat.
Go ahead, read it to me, or I can't.
What % of the atmosphere is carbon dioxide?
It's 0.04%, and is measured in 400. Now it's probably 420 parts per million.
Thank you. Doesn't seem like much.
No, it's not. But what I try to show you in that graph is because it's intercepting the biggest flow of heat away from the Earth's surface, it has sort of an outsized effect on the Earth's climate, which is what has got everybody concerned. But the issue is, I think they said, well, if CO2 can do this, then everything gets blamed on CO2, instead of looking at other heat trapping dynamics, which as an ecologist is what I was trying to look at, is what are these other different things? James Hansen, who was sort of the spark plug to push this whole global warming issue, he's learned to study climate looking at planets with no water, no life, no oceans. And so all he looked at was atmospheric chemistry. I like to think ecologists are a step higher than that. As I had to study what was happening to wildlife in the Sierra Nevada, I had to understand climates, El Niños, La Niñas would cause droughts and floods, but I also had to understand how we screwed up the hydrology, how we affected the forest, how we've affected wildlife. So I've just been trained to look at many different things. So I don't easily grab on to just the one idea that it's all CO2. All right, can I proceed, or you got another question?
I don't see any other question here.
All right. Let's make sure I can do this right. All right, we all got it? Okay, so now let's check. Every time people see a heat wave, they oh, this is climate crisis caused by CO2, but it's a very different effect. In contrast to the greenhouse effect, extreme heat waves are caused by heat domes that operate in a manner similar to commercial greenhouses or a car with its windows raised. For your car, the temperature is determined by how long the air is trapped inside the car. The longer the windows are up during a midday sunshine, the higher the temperature rises. So at midday, in 80-degree Fahrenheit heat, temperatures inside your car can rise another 43 degrees to 123 degrees Fahrenheit in just 1 hour. And tragically, not realizing how quickly heat can accumulate, pets and children left in cars will sometimes die from extreme heat. And thus you have these public service announcements trying to make people aware. Now, to reach 123 degrees Fahrenheit, the car's rate of energy gain is at least 154 watts per meter squared for an hour. In contrast, the increased CO2 has only added about 2 watts per meter squared over the past 100 years. So it would be silly to argue that higher CO2 increased the car's extreme temperatures, but not how long the windows were raised. So just lowering the windows would eliminate the extreme heat. And just how long a heat dome persists is a lot of the reasons that we have these extreme heat temperatures. So the important dynamic I want you to make sure you grasp is it's suppressed convection that causes extreme temperatures. Now, I was taught in 8th grade about the 3 ways heat is transported. Solar radiation traveling through empty space heats the Earth's surface. Then the ground sheds that heat in all 3 ways, mostly by emitting the whole spectrum of long-wave radiation that I just discussed. Heat is also transferred to cooler air when the air contacts the heating ground. And thirdly, there's convection. When warmed air becomes less dense, it rises and it carries heated air towards the stratosphere. And without convection, the Earth's surface would trap surface heat like a car with its windows raised. And convection, it not only causes warmer air to rise, but allows cooler air from the higher altitudes to sink. And the mixing of the cooler air from above further reduces our surface air temperatures. Now, the global average temperature, in a way, is inappropriate name because it's based on measurements only taken about 6 feet above the ground. But when we're debating the Earth's energy imbalances and the climate heating, the whole atmosphere really should be considered. So convection carries warm air up to the stratosphere, where CO2 also has a cooling effect. You can see where the stratosphere begins if you see a rising rain cloud. It gets up to where the stratosphere starts to warm and the rain cloud flattens out. And as it reaches an altitude that we call the tropopause. At that altitude, the air is probably about 100 degrees cooler than the ground, and the air cooled down to, in that area is cooled down to 2 dynamics. First, lower air pressure causes lower temperatures. It doesn't take away the energy, but it's a function of temperature. Second, the air cools as greenhouse gases more easily can radiate heat back to space in the stratosphere's thinner atmosphere. However, if the air doesn't radiate heat away, the cooler air would warm back to its original temperature if it sank and air pressure increased. So the average person rarely asks, how does 99% of the air molecules that are not greenhouse gases, mostly oxygen and nitrogen, how do they radiate away all the heat they've absorbed after contacting the ground or colliding with other heated molecules? And I'll give you the answer in a second. So the stratosphere spans an altitude between 15 and 80 kilometers above the Earth. At 35 kilometers, the stratosphere's air density becomes as thin as Mars. It allows infrared heat to escape as easily as Mars cooled. Furthermore, clickbait media rarely informs the public about CO2's essential cooling effect. Because heated oxygen and nitrogen are not greenhouse gases, they can only get rid of that heat that they've acquired by colliding with CO2 or another greenhouse gas and transferring its heat to CO2. CO2 can then radiate the heat away. So without a greenhouse gas to radiate heat away, our atmosphere would be experiencing runaway warming. Oxygen and nitrogen would keep accumulating the heat. So climate scientists predicted decades ago when they talked about the warming, and satellites are now observing this, that as CO2 increases, the stratosphere is cooling twice as fast as the lower atmosphere is warming. Now, heat waves happen when heated air is denied access to the stratosphere and above in CO2's cooling effect. So you look at a heat wave, it's caused by suppressed convection in the lowest 6 kilometers of the atmosphere. That prevents rising heat from reaching the stratosphere where greenhouse gases can cool the air radiatively. Heat domes trap heat for days. They are high pressure systems, usually caused by the jet stream and causing sinking air to inhibit upward convection. In addition, when you have these high pressure systems, they reduce cloud cover further. You have clear skies, which increases solar heating. And for example, in June 2021, Canada reached its highest record temperatures, and it was set and then reset and reset again 3 days in a row at the end of June 2021, when a heat dome stalled for days over Lytton, British Columbia. Canada's final record temperature was 45 degrees Fahrenheit warmer than Lytton's average maximum for the month of June. And that's a heated difference that's intriguingly similar to the increased temperature of her car with its windows raised. But southwestern Canada's heat wave was caused by an exaggerated ridge that you see here in the jet stream known as an omega block. And these have been talked about for at least 7 decades that I know of. And what happens is when you have this omega block, the jet stream can't move the high pressure system eastward, and so it stalls. So as the block remained in place for days, more heat got trapped and accumulated, driving Canada's record temperature higher and higher for 3 days. Now, then I look at clickbait media understanding the science, and I see they clearly don't understand geography or climate science. CNN ranted that this very local heat dome was evidence that CO2 climate change is frying the whole northern hemisphere, but it was only a very local event. And furthermore, science doesn't support CNN's rant because climate models have all suggested that any greenhouse warming should reduce such blocking events. And finally, I want us to consider the trends in the United States based on EPA data. The worst heat waves happened in the 1930s. As you can see from EPA data here, there is no correlation with rising CO2. All the hype by politicians and the media that heat waves are evidence of a CO2-driven climate crisis is really unsupported fear-mongering. All right, I'll take questions for another 5 minutes. And I can't hear people. No questions?
No, there's there is some questions in the chat.
Oh, please read them. I can't see them.
It's from John Barry. Are the predictions of sea level rising exaggerated? And the other one, are the other changes like to our usual weather patterns overrated? And John Barry is the one that asked.
Okay, I pretty much think they are. If you look at sea level, what we've used is tide gauges. And so you got a measure of relative sea level. You don't know if the land is sinking or the ocean is rising. And then our computer models were kind of tuned to match whatever the tide gauges were telling us. Now, there was a study that was just released maybe 3 or 4 years ago, where we're now with GPS stuff, we can measure how the land is changing using satellites and see if the land is sinking or rising. So that study showed that sea level rise was only going about 1 millimeter if you accounted for the land sinking. And this was all from Australia and Indonesia and around those areas. We also know from studies on the East Coast that is kind of caused, is the heavy ice sheet that sat in Canada kind of pushed down on the land, and around about the Canadian-US border, it was like a fulcrum point, and the American coastland rose. And then as the ice sheet melted, along the coast began to sink. And so that has caused some of the sea level rise we see along the East Coast is due to this, what we call isostatic glacial rebound of the East Coast sinking. Plus, what we're doing now is we're overdrafting all the subsurface water. And so there's some places like New Orleans was originally above ground. It's subtracted, it screwed up the hydrology, subsurface water was lessened, the land collapsed, so you sunk. There's places around Thailand and Indonesia, the land has been sinking like 15 centimeters a year. It's some incredible amounts of stuff. So the problem is that you blame it all on CO2 and you don't look at all these other dynamics that are going on. Sea level rise is getting misdirected. And part of it, I'll talk about Antarctica in a little bit. That's another issue. They just say, well, because Antarctica must be melting, we must be getting more sea level rise.
Thank you, Jim. Before, I think Jay raised his hand, but before this, I think I interrupted someone when I was reading the chat. Someone was asking you a question. Was it Al? I'm not sure. Well, then Jay, why don't you go ahead?
Yeah, regarding the CNN rant, was it just newscasters carrying on, or were there a group of scientists that were making a presentation? And if so, is there some specific contradictions between what you're saying and what they said?
You know, sometimes it's just the journalist making a generalized statement. You know, I say clickbait media, you don't attract attention if you just say everything's okay. The kind of catastrophes draw us in for good or bad reasons. But a number of media reports report published scientific studies. And the problem is a lot of times what these studies are based on models, and they're providing plausible speculation, not necessarily an observed observation. So and what I see the media doing way too often is they'll focus on this catastrophic speculation, and they ignore it. And I've read thousands of papers in my years of doing this. In 25 years of director of the field station, I was reading everything I could to understand what was affecting my wildlife up there. And there's a lot of people that just say, I don't see the problem yet. And it's not being fairly or objectively balanced on what are the causes going on. And I don't know how many people ever heard about the negative greenhouse effect in Antarctica that I mentioned. My guess is I'll be surprised if more than one person here ever heard of that, because the media doesn't cover that kind of stuff. So I think that's what, hopefully if you develop some good critical thinking skills and look at multiple hypotheses, you can cut through what the journalists are doing. And there's some good stuff and there's some distorted stuff.
Len Rothman, I think it's your turn.
Thank you so much for what you're revealing to us this time. I may have missed this. I was in a couple of minutes late. What do you think is the methane story, the automobile exhaust story, the relevance of these things and other things that go in the atmosphere?
You know, I became a strong environmentalist because you could see air pollution, you could see water pollution, and you could separate that from what would naturally happen. So that kind of pollution you want to stop. So if you have dirty emissions, that's an issue. Whether methane and CO2 is causing these climate crises, that I don't see so easily. And the more I look at it, the more I feel like there's other dynamics that we're conflating with CO2's greenhouse effect. So, you know, in the inner city, to go to electric vehicles instead of fossil fuels makes a lot of sense because you don't have that congested kind of pollution in the city. You know, in the country, I don't see that as a problem at all. And the only thing I worry about is sometimes when government mandates force things to happen too quickly, like before our electrical grid is capable of taking on these challenges, that we're going to cause some major problems. And so, you know, that's where I leave it. I'm not really afraid of a climate crisis at this point. You know, I might be proven wrong, but the more I research it, the more I become more skeptical.
You mentioned water problem. The San Joaquin Valley in many areas is supposedly dropping because they're sucking so much water out of the aquifers.
Oh, absolutely.
And the other problem is the water crisis doesn't seem to be addressed to the people that need water for the agriculture, such as mandating 100% drip irrigation, mandating fines for perhaps for growing stuff which is not vitally necessary, not investing in desalinization plants and enforcing that water at its high price to go to agriculture. Basically, I feel we're causing much of this water problem by trying to keep the bread prices down so people will get reelected.
Yeah, you know, we're getting a little off topic here, but I agree. I'm a big fan of desalinization. I think if we can use that, especially for not just agriculture, but the cities, so we're not ruining the water that's running through the rivers for fisheries and whatever. And I think I get a little nervous of what kind of minor things to mandate, but I would try to mandate that if you're taking this water, you try to recharge the aquifers. And there's ways to do that. And I think that would be some of the most important things we could do. Somebody else?
I think Alfred has been patiently waiting. Alfred, picture.
Yes, we're probably most concerned about how weather affects us. I live and I've lived for decades in the western part of San Francisco, and my impression over the last several years is the weather here is definitely cooling. I see so few sunny days in the summer and even during the whole year. Do you agree? And if so, what is your answer to that?
Well, certainly this year has been colder. It's like, usually I look forward to spring and it's just been overcast and cool, you know, and it gets a little complicated because as you have this cold current coming down the California coast, the westerly winds bring the little cooler air to us and we get the fog, and that kind of cools our temperature. You go a little further inland and you don't get that fog, so you don't have that kind of coolness. So you have very different local impacts that are going on. When I had a meadow, I was studying 6 meadows in the Sierra Nevada, and one of them collapsed and it dried out and the wildlife was leaving. And people came and said, oh, that's just what climate change suggested. Well, I looked into all the data, and Northern California actually had hotter maximum temperatures in the 1930s. But we've had warmer minimum temperatures, which often are a cause of urban greenhouse effect, urbanization, and us eliminating wetlands. So it's a complicated issue, but you know, your perception is partly going to be driven by El Niños and La Niñas and a longer range oscillations called the Pacific Decadal Oscillation that affects our climate. Any other questions?
I may have a kind of a tongue-in-cheek question, but I can wait until the end of if you want to continue.
Okay, let me do this last one and then I'll just go forever. All right, so finally, heat trapped in the ocean. It now serves as a hot water bottle that helps to warm our climate. No matter at what depth heat is absorbed into the ocean, that heat is trapped there until it rises to the ocean's micron thick skin surface layer. And if you, just to remind you, 1,000 microns can fit on the tip of a pencil. So there's this very thin layer that controls how much heat can escape the ocean. Now, it's not greenhouse heating, but it's heated, salty subsurface water that remains too dense to rise through a freshwater layer from rainfall or whatever and reach that skin surface where the heat can be ventilated. So wherever ocean salinity gradients form with fresher water at the surface and saltier water below it, there the greatest amount of heat gets trapped. Now, you might understand this better by understanding solar ponds. Now, humans have taken advantage of the salinity effect and have created low-tech, low-maintenance solar ponds that generate inexpensive heat to warm buildings and greenhouses and generate small-scale electrical power. I know the Israelis have been big into this. University of El Paso has been looking into this. It's hard to make it large scale, but it can work on small scales. Functional solar ponds. All they have to do is maintain a bottom layer of dense salty water at about 6 to 10 feet depth. And that's where solar heating is the greatest before it starts dissipating. And that penetrating solar radiation raises the pond's bottom layer temperature as high as 190 degrees Fahrenheit, despite air temperatures are only 68 degrees. So the only cost of solar pond heating is maintaining this upper freshwater layer and a dense salty bottom layer and then transporting that heat. So on small scales, this is very promising, but it also gives you insight into how heat gets trapped in the ocean. And we have these natural heat trapping salinity gradients that occur in the ocean from the tropics to the Arctic. Now, here is a little confusing graphic. I'll try to walk you through it, but it's data from surveys in tropical oceans. So you get winds and currents that create a well-mixed layer in the upper 20 to 40 meters illustrated in the yellow. That layer has uniform salinity throughout, represented by this blue line. And the mixed layer also has homogeneous temperature, represented by the black line. But between 40 and 70 meters depth, illustrated by the orange layer, the increasing salinity traps solar energy and increases temperatures where we otherwise expect cooler temperatures because solar heating declines with depth. Now, oceanographers call this layer the barrier layer because it stores heat and prevents colder, deeper waters from mixing with the surface layers. So hurricanes and typhoons, they usually intensify when they pass over a barrier layer because the barrier layer prevents cooler water from below the blue layer from being sucked up to the surface and weakening the storms. Yet the micron thick skin surface layer remains cooler than the mixed layer because it's constantly radiating away any absorbed greenhouse infrared heat plus any absorbed solar heat. And it also loses heat due to evaporation. So this cooling of the skin layer happens faster than the mixed layer can bring solar heated subsurface water to the surface, which causes solar heated water to get trapped. So although energy measured in watts per meter squared, for all energy, different wavelengths behave very differently. While the sun's shortwave energy, represented here in yellow, penetrates the ocean as deep as 100 meters, the Earth's greenhouse long-wave infrared energy, in red, never penetrates any deeper than a few microns of the ocean's cool skin surface. Now, it studies looking at the cool skin surface dynamics. They find no obvious mechanism that can demonstrate how greenhouse infrared heat can significantly warm a solar pond or the ocean. Often when they say greenhouse gases are warming the ocean, they're just making an assumption in a narrative that they don't have scientific studies to back up. Now, in a recent tropical ocean study, they measured 410 watts of long-wave greenhouse infrared being redirected down to the ocean skin surface. Immediately below the cool surface skin layer, the water had been heated by about 67 watts per meter square of solar shortwave energy. But that subsurface layer was still warmer than the skin layer that was absorbing all that greenhouse infrared. And the reason for that is because the cool skin surface is immediately radiating away that heat. The heat emitted from the skin layer accounted for all the incoming greenhouse heat, plus the solar heat that had risen by convection or conduction to the skin layer. The ocean's ability to store solar heat at depth is what creates the warm water that is stored during La Nina-like conditions and released during El Nino. Now, due to the salty water transported by the trade winds from regions of high evaporation, trapped tropical heat forms the Earth's greatest reservoir of heat, the Western Pacific warm pool. The warm pool grows during La Nina-like conditions as stronger trade winds sweep more heated surface waters westward, and they traps that heated water down as deep as 200 meters. Now, simultaneously, colder deep water upwells in the Eastern Pacific to replace the removed surface water. The cooler ocean surface reduces cloud cover, which then increases the whole solar heating of that water. It then gets transported over to the warm pool. Now, the interesting thing about this is this trapping and ventilating of heat in the Pacific Ocean warm pool creates a temperature paradox that really confuses most people. El Nino events ventilate some of the stored warm pool water, producing warm spikes in the global average air temperature, events indicated here by my red arrows. Although the ventilating heat during an El Nino event increases the average global air temperature, as you see in these temperature spikes, El Ninos are actually cooling our oceans and cooling the Earth's climate. The opposite happens during a La Nina-like conditions. Due to more upwelled cooled water during La Nina-like conditions, the global average air temperature drops, even though more cloudless skies are paradoxically adding more heat to the ocean and warming the climate system. Now, in addition to this, heated tropical waters are transported around the world and modulate the rest of the Earth's climate. Scientific studies have determined that in the Eastern Pacific and similarly in the Eastern Atlantic, the regions illustrated here in dark blue, due to La Nina-like conditions, the oceans absorb the greatest amount of solar heat, but they don't release it there. They release most of that heat elsewhere. The regions illustrated in red represent where most of that trapped heat eventually ventilates. Ventilating heat at those latitudes warms those regions several degrees higher than possible if there was no transported ocean heat. Measurements of heat from the Gulf Stream have determined that over 150 watts per meter squared of additional heat is released from the Gulf Stream into the atmosphere. That warms the westerly winds, which make Western Europe's winters milder than similar latitudes in North America by as much as 27 to 36 degrees Fahrenheit. And heat remaining in the Gulf Stream is then transported into the Arctic Ocean, controlling sea ice and Arctic air temperatures. The remaining trapped heat enters the Arctic via the North Atlantic current, represented here in red. The tremendous amount of tropical heat entering the Arctic prevents winter sea ice, from forming along northern Scandinavia and the adjacent Barents Sea. Now, this is a satellite-based illustration and depicting the maximum winter sea ice extent for the year 2020. The yellow line represents the 20th century average maximum extent of sea ice, which has indeed retreated some. Now, my superimposed red circle here identifies the Arctic Circle. And notice winters are naturally cold enough to form sea ice outside the Arctic Circle, as seen in the Hudson Bay or in the Bering Sea. In contrast, inside the Arctic Circle, the only area without sea ice is where warm Atlantic water is entering. Now, if I expand the circle south to 55 degrees latitude, so it encompasses latitudes where cold winter air temperatures normally freeze the Hudson Bay, we see extensive open water along the pathways of transported tropical Atlantic heat where warm Pacific waters have reached the Bering Sea. The amount of Atlantic heat eventually reaching northern Asian coasts is not enough to extensively melt all the sea ice directly, but the heat does thin the ice, and it thins it enough so it readily melts in the summer sun to form life-giving open water. In addition, more open water along the Asian coast has been created when you have freezing winds blowing from Siberia that can still drive ice out of the Arctic and into the warmer Atlantic. And not all the inflowing heat ventilates. There's layers of warm, salty Atlantic water that persist between 100 and 900 meters depth in the Arctic Ocean. And that trapped heat is capable of melting all the Arctic sea ice several times over, as has been recently measured. Incoming warm Atlantic water remains in the Arctic Ocean for 25 to 30 years. However, again, clickbait media and alarmist politicians, and I put Al Gore firmly in that camp, calling the oceans, saying the oceans are boiling. They have ignored the heat transported by these ocean currents and instead have blamed the rising CO2 for any Arctic warming and loss of sea ice. But such a blinkered belief embarrassed Al Gore and a few prominent scientists who wrongly predicted that the Arctic sea ice would disappear due to CO2 by 2013. And nonetheless, some scientists keep making those predictions of a loss of sea ice, but they just keep extending the date out for total loss further into the future. Now, in contrast to people thinking this is catastrophic loss of ice, based on their predictions, less sea ice is usually a very good thing for Arctic ecosystems. Several studies have documented and reported and published that the phytoplankton that serve as the base of the Arctic food chains have dramatically increased as sea ice has dwindled. Clearly, less ice and more open water allows more photosynthesis. More photosynthesis, more plankton, which sustain more fish, which sustain more ringed seals, which sustain the polar bear populations. In this illustration of Arctic sea ice in 2012, the purple color represents first-year ice thinned by inflows of warm Atlantic water. The white and the yellow colors represent older, thick ice that has been trapped for years in the Arctic by the clockwise circulation that pushes ice up against northern Greenland and the Canadian archipelago. By August, most of the first-year ice has melted, creating open water for more photosynthesis. Furthermore, first-year ice is essential for the ringed seals that sustain the polar bear. Most ringed seals remain in the Arctic all year. Ringed seals survive there only by creating several breathing holes in the ice. They create those holes by busting through newly forming thin ice with their heads and then gnawing at the edges continuously to keep the breathing holes open. It is the new thin ice that forms each winter in the Hudson Bay that makes it such a hotspot for seals and polar bears. In contrast, regions with old ice are too thick to initiate breathing hole creation. Thus, the seals and the bears are very sparse in those regions. And finally, scientists have measured the energy released by ventilation of trapped heat through various thicknesses of Arctic sea ice. And here again, thin first-year ice is colored purple and has the lowest ability to insulate stored heat. A 2002 peer-reviewed paper found open Arctic waters ventilate 700 watts per meter squared compared to CO2's global average warming of just 2 watts per meter squared of added energy. After a month of fall temperatures, new Arctic sea ice thickens to about 1 to 2 meters, yet it still ventilates 80 watts per meter squared of heat. And even after reaching the typical maximum of 2 to 3 meters thickness, first-year ice still ventilates 10 watts per meter squared, or 5 times the energy produced from increased concentrations of CO2. In contrast, older thick ice ventilates very little heat, and accordingly, before the shifting winds of the Arctic Oscillation blew thick older ice out of the Arctic, scientists found no warming in the Western Arctic from 1950 to 1990. So the question is warmer Arctic Ocean evidence of oceans releasing stored heat, or is it evidence of impending doom from CO2 warming? The ventilation of oceans explains the Arctic Oceans, why scientists observe that the rate of Arctic winter temperatures is warming at a rate far above the global average, while in North America and Eurasia's winters, there's cooling trends have been observed. The melting of sea ice by ventilating heat is too often incorrectly blamed on rising CO2, despite the fact that polar regions experience very limited greenhouse warming. So I'm going to conclude that undeniably, there are scientifically proven complex dynamics that trap heat and drive warmer temperatures in extreme weather, in addition to rising CO2. A CO2-driven climate crisis is just one theory. And if you follow all the science, not just the fear-mongering narratives that has been promoted by clickbait media, my guess is you'll sleep much better knowing claims of a climate crisis is just one theory placed upon good scientific data. Thank you.